Hello, I'm Enyi from IRAP in Toulouse, and I'm a second-year PhD student. I'm glad to here to present my work on dust evolution in the forming prestellar core L1506C. So we already heard several talks about dust in the past 2 days, but I still want to address why do we need to study dust. So the early stage of star formation is usually studied with far infrared and millimeter dust emission. So the dust properties, they will influence the cloud property estimates. So it's very important that we understand the dust thoroughly. And we know dust is the basic component for planets, and studies show that grain growth already starts at an early stage, even before the protostellar stage. And our target, L1506C, is part of the filament L1506 in the Taurus molecular cloud. It's still at a very early stage. So it's still in the process of forming a prestellar core, but it already shows evidence of grain growth, so very suitable for our study. And for our study, we have data of various wavelengths. We have dust emission at far infrared and sub-millimeter wavelengths at 4 Herschel bands. And we have new NIKA2 observations in millimeter. And we also have extinction observations in the VIRCAM JHK bands. And we also have scattering observation in speed of 3.6 micron. So with all these dust emission data, we did modified blackbody fits to both the maps and to the core SSEDs. And then we did 3D radiative transfer modeling with the software SOC. To do the modeling, we use the recent THEMIS2 dust models. So here on the right, you can see an illustration of dust evolution in the framework of THEMIS1. So beginning in the diffuse interstellar medium, grains gradually start to grow a second mantle, and then they coagulate together and finally form aggregates with a surrounding ice mantle in the dense ISM. So for our modeling, we use both diffuse interstellar medium type dusts, like here in the above, but in THEMIS2, they are spheroidal rather than spherical. And we use the spherical icy porous evolved grains, which mimic these aggregates at the bottom, because aggregates are not yet available for THEMIS2. And here on the left, you can see the plots of the dust mass extinction coefficient kappa for the diffuse dust and for evolved dust at different size distributions. So you can see, as expected, the evolved grains are more emissive than diffuse type dust. And before the analysis, one very important step to do is to reconstruct the extended emission that can be observed by Herschel, but not with NIKA2, which is a ground-based telescope. So in that way, we can really combine Herschel and NIKA2 observations. So to do this, we first use the software scanner NIKA to reduce the NIKA2 data. And then we reconstruct these extended emission by using the Planck observations, which are predicted at 36 arcsecond resolution with machine learning methods. So on the figures, you can see after reconstruction, the NIKA2 images, they are much brighter, and these reconstructed maps are what we use in the analysis that I will present. And well, I don't have time to explain the details of the reconstruction, but if you're interested, we can discuss it in more details later. So now here I present you the result of the modified blackbody fits. So to do these MBB fits, I fit SEDs of each pixel with the MBB function, where intensity is assumed to be proportional to frequency over beta times the blackbody function, where beta is the important dust spectral index. And we only looked at pixels with signal-to-noise ratio larger than 4 at all wavelengths. So here on the resulting T-beta maps, you can see that temperature decreases from like 15, 16 Kelvin outwards to 11K in the center, and beta increases from like 1.41, like as in diffuse ISM, to 1.7 in the center. And we did the MBB fits with both chi-square minimization and a hierarchical Bayesian method. I plotted beta against temperature for both methods here on the right and fitted different slopes. And you can see this anti-correlation is present for both methods. And it means that we have real anti-correlation due to real intrinsic dust properties. And then based on the T and beta maps I showed before, we calculated the column density NH2 maps with this equation. And for kappa used in this equation, where the reference kappa 0 was taken from back with 1990, well, I will call it B90 later. And the frequency is used at 250 micron. So here on the right, on the NH2 map, you can see that L15060 is fragmented into two cores. And I fitted two ellipses based on the NH2 contour to represent these two cores. And then I also defined an envelope area around the cores, defined within this black contour. And then we also defined a surrounding filament surrounding the cores and envelope. But because this envelope area has a low S over N on NIKA2 maps, it is defined based on Herschel intensity maps. And then we did a part of photometry to all these structures so that we can exclude the warm material along the line of sight. So unlike the MBB fits for the maps. And the resulting SEDs and the fitted MBB function for the structures are shown here on the left. So you can see that for the two cores, they have similar dust properties, like temperature of 11K and beta around 1.9. But the envelope and filament, they have clearly higher temperature and lower beta. So this significant change of beta shows that we might have a grain growth in the center of the cores. And we see a sequence of dust evolution from the outer filaments towards the central cores. And this trend is the same as what we saw on the maps. But of course, here the temperature is lower for the cores and betas are higher because of a part of photometry. And on the right in the table, you can see the densities and masses for the two cores. Here I present results using either the B90 kappa or the Themis 2 evolved grains kappa. And for both kappas, you can see the volume density is smaller than 5 times 10 to the 4, and column density is smaller than 6 times 10 to the 21. So our cores are not very dense. And they both have masses smaller than their gene's mass, meaning that our cores are really at early stage and are not yet collapsing. So now we move on to the radiative transfer modeling. For people who don't know SOC, here's an illustration of how it works. SOC takes inputs as the Herschel and NIKA2 observations. And also there are some other input parameters that are user-defined. And I will go into details in these in my next slide. And then based on these inputs, SOC fits two parameters, the strength of the radiation field G0 and the column density NH2. And as outputs, SOC gives the emission maps, NH2 maps, extinction maps, and the 3D volume density and temperature distributions. And we compare these outputs with observations. So to find out which input parameters describe our target the best, we use a strategy of an input parameter grid. And there are five parameters in our grid. The first two define the cloud density profile. which is a plumber-like function. And AV, it describes the attenuation of external radiation field. N0 describes where the diffuse type dust, where the transition between diffuse type dust and evolved grains happens. And finally, A0, it is the peak of the log normal size distribution of evolved grains. And this parameter mainly regulates the kappa of evolved grains. So we did modeling of all combinations within our parameter grid. And indeed, it is not easy to find the best parameters because some of the parameters, they are degenerate. For example, for N0, all these three parameters, they give good results. But in the end, with compromises between the observations, we decided to select these parameters that are marked in red. And I will present the results using these parameters. So here in this figure, you can see the modeled emission. In the first row, you see the observations at different wavelengths. Second row shows the modeled emission. Third row shows the residuals. And in the last row, I plot the residuals at each pixel as a histogram. And I divided the residuals into two areas, the cores, envelope, and filament. So looking at the three central Herschel wavelengths where they were used for the fitting, the residuals are all smaller than 10%. So it's expected, and we have good fits for these. But if we look at the other three wavelengths, I fitted for the core residual histogram Gaussian function, and their peak position and standard deviation are shown here on the right. So for 160, we have residual around 20%, and for the millimeter, they are 10% or less. So in principle, we can say we have good fits for the cores. They are especially good for millimeter. But the situation with the filaments and envelope is more complex, partly because they have lower signal-to-noise ratio. For example, the filament residual here at 160 is asymmetric, and it is maybe it's because of anisotropic radiation field, or it's because we have a cloud shape it's more complex, but it's hard to test these hypotheses with our current model. So then here in this figure, you can see the modeled column density map, and the white contour here shows the fraction of dust along the line of sight that is in evolved grains. So if we compare the results with the MB modeling, the maximum NH2, modeled NH2 is about 1.3 times 10 to the 22, and it's 1.7 times larger than MBB modeling results. And this 1.7 is even just a lower limit because the B90 kappa we used for MB modeling is smaller than the kappa of Themis2 that we use for SOC modeling. And the modeled minimum temperature is 8 Kelvin, which is 3 Kelvin lower than MB modeling results. So these differences means that even if we don't have a very dense core, and even if we don't have a internal illuminating source, radiative transfer effects is not negligible. And our modeled maximum NH2 is consistent with other independent measurements of N2H plus emission. And if we look at the contours, you can see that the central part of L1506C is dominated by evolved grains by over 80%. And even in the filament, 50% of dust is in evolved grains. So these are direct evidence that we have grain growth, and even at this early stage where collapsing is not happening. Here you can see the modeled extinction results compared with observation from RealCam. Here on the right, I plot the modeled J-band extinction against the RealCam observation for each 2-mass star that was used to calculate the observations. And because the star density, the 2-mass star density in the core center decrease, so the RealCam observation observed map might not be accurate. So when I fit the slope to my data point, I exclude these data points in the core centers. So this fitted slope is 1.8. And from the residual map, you can also see that our model overestimates the extinction by a factor larger than 2.5. It is sadly the case for all combinations within our grid, and we cannot do better than that. But this overestimation has also been found in previous literatures. For example, in previous modeling with stock in the core LD in 1642, also in the Taurus cloud. But the authors, they managed to decrease this overestimation by increasing the optical depth ratio between far infrared and J-band, by not changing any other parameters. So improved by that, we also checked the tau ratio of our target, and the result shows that the observed tau ratio is actually really larger than both the evolved grain model and diffuse ISM type model we use. So this improves, this means that we need to use dust models with a higher tau ratio. So either dust models that are more emissive and or less absorbing. And then in the end, you can see here the modeled scattered emission. So with Spitzer, a core shine, so enhancement of scattered emission of level 0.04 is observed for F1506E. And with our modeled maximum scatter intensity of around 0.03, we can reproduce the observed scattered emission within 1 sigma. So now here I arrive at my conclusions. So with our study, we show that F1506E is fragmented into 2 cores that are still in the process of forming a prestellar core. And we need porous ice-coated grains that are more evolved than the diffuse type dust to reproduce the observations. And having both emission and extinction, they put strong constraint on 3D modeling and dust models. So in the future, we will explore different grain properties within the framework of Themis dust models, especially to improve our extinction modeling. And we have some independent gas tracers of L1506E. We want to use them to investigate accretion and cloud structure, like the volume density for this target. And then in the rest of my PhD, I will extend this study to other prestellar cores in different clouds. So now we already have a catalog around 10 targets. So thank you for your listening, and if you have questions.
Thank you. So other question for you?
So you see grain growth, if I understood correctly. So I'm not a specialist, so naively, the peak of the distribution of the grains is evolving from which size to which size?
So the grain size of evolved grains, they are around, they are between 0.1 micron and 0.7 micron. So with grain growth, I mean, there are grains with 0.1 micron size that are present. So they are already certainly larger than the diffuse type dust in diffuse ISM.
So does it mean that the isolated grains are accreted together? And so from going from 0.1 to 1.5, you get...
No, like 0.1 is already size of grown dust. So because we have a size distribution, it's we don't have grains with one certain size. We have distribution of different sizes, and 0.1 micron, it is already size of grown dust. Well, it's not as grown as like in disks, but
but my question is, in the big grains,
yeah.
how many small grains do you have? 1,000?
Like in one, here, like in one big dust, it
Yes.
consists of one small carbon ring and 3 small silicate grain. And you can consider this as a basic component to form aggregates, and you stick this kind of main composition together to form larger grains. And
Yeah,
you
but
may
my
have
question is more quantitatively speaking, how many you get porous grains, so I have no idea how many in the end such brick you get.
Hundreds. Well, it can grow as large as it wants before it breaks.
Okay, last quick question.
Yeah, I was curious, when you do your radiative transfer modeling, you say you have a transition between the diffuse dust and your aggregate. So is it a sharp transition, or do you kind of smooth it?
No, it's not. We use a fractional abundance, the function. Basically, it looks like this from diffuse to evolved. The fraction, it's a smooth transition like this.